One of the most exciting developments in the last decade in astronomy is the discovery and identification of objects located within the solar system but are of interstellar origin. This opens the way for further investigation of these objects and the opportunity to learn about their formation in other star systems entirely that could yield important clues about the formation of our own solar system, but also the formation of star systems across the galaxy. And they may even shed light on the question of astrobiology. There are several important points on this count. The first is that a sampling of interstellar objects could give us an insight on the so-called phosphorus problem. This is an issue in the question of life in the universe, in that DNA is heavily dependent on the presence and availability of phosphorus. As far as life on Earth is concerned, if we had no phosphorus, as far as we can tell, there would be no life on this world. There has been a contentious debate over whether arsenic could perform similar functions for life in the absence of phosphorus. But the reality is that if it could, it would not be as good. And the general consensus right now is that it's not a very likely scenario, at least without all sorts of chemical acrobatics to make it work. But phosphorus is tricky. In fact, it's almost spooky as to how tricky it is. Life on Earth depends on 6 chemical elements. These are carbon, hydrogen, nitrogen, oxygen, sulfur, and phosphorus. These elements make up a large percentage of the human body. Most of those elements aren't a problem in the universe. We watch certain classes of stars belch out carbon all the time. Hydrogen is the most abundant element in the universe. We see oxygen all over and so on. But phosphorus stands alone. It may not be that common. At its most basic, phosphorus in the form of adenosine triphosphate is what allows cells to store and transfer energy. It's absolutely crucial to life on Earth. Phosphorus in the universe, like many heavier elements, is formed in supernovae, the process and evolution of which populates the universe with those materials. Computer models have shown that phosphorus generation should be straightforward and it should be everywhere. The problem is, we don't see that. This alone could solve the Fermi paradox hands down, explain the Great Silence, and simultaneously give us a key to search for rare alien life: follow the phosphorus. The problem is that when studying supernova remnants, the amount of phosphorus present seems to vary wildly. Some remnants have lots of it, some seemingly do not, raising questions about phosphorus distribution in the Milky Way. This may mean that only certain types of supernovae, created by rare types of supermassive stars, can produce phosphorus. But the problem doesn't end there. To get phosphorus onto a planet's surface in a form that the chemistry of life can use is rather limited. Phosphorus in the solar system is found in meteorites in a suitable form, and that was probably how the initial phosphorus used by protobiological processes in abiogenesis got here in the first place. So you may need the right kind of supernova and abundant enough meteorites to deliver the phosphorus to an exoplanet. Then that exoplanet must be habitable, and there are likely further conditions that need to be met. This ranges from the presence of a moon — it's been suggested that life may not happen without one — to a much more newer hypothesis that you need porosity in the upper parts of a planet's crust, introduced by sufficient impact bombardment for life to arise and be protected during the early years of a planet's life. By studying interstellar objects, we can determine just how common phosphorus really is in the galaxy. If we get a sampling of, say, 100 interstellar objects, and they all have plenty of phosphorus, then this won't be so much of an issue. If we find that a significant portion of them are lacking phosphorus, then life in the universe has a problem. Studying the composition of interstellar objects will also yield clues on the abundances of other elements in the Milky Way, and give us a profile of other worlds from the comfort of our own solar system. But we may even be able to do it from the comfort of home, as on the surface of the Earth. We know of at least 2 interstellar objects so far in space, Oumuamua and Comet Borisov. But there are also 2 candidates for captured comets in the solar system that may originally have been of interstellar origin and were captured by Jupiter. If those are in fact of interstellar origin, then we already have a ready source for materials to study. We just need to go get them and do a sample return mission. But it could be easier than that. If there is indeed a large amount of interstellar material moving through the solar system at any given time, and the indications so far support that, then meteorites of interstellar origin do hit Earth, and our planet is already a source for interstellar materials. Indeed, some of the anomalous meteorites found in collections worldwide may in fact be of interstellar origin. But there is another option. It seems as though we've already detected a meteorite of interstellar origin in the act of falling to Earth. This should not be surprising. Oumuamua and Borisov were spotted fairly close together in time, which implies that interstellar objects of that size are not rare. It stands to reason that even smaller objects should be more abundant, as is the case with our solar system. We see tons of meteors, both sporadic and in showers, showing that dust is very common in the solar system. Likewise, tons of meteorite material falls on Earth each year and makes it to the surface, also confirming abundances of small objects. Yet we very rarely get hit with large objects. It happens, much to the chagrin of the dinosaurs, but not very often because large objects are lesser in number. So a meteorite of interstellar origin should not be surprising. In a paper by Siraj and Loeb, linked below, they detail that in a search of the CNEOS catalog of bolide events, they found a meteorite entry of sufficient speed to have been on an unbound hyperbolic trajectory, the hallmark of interstellar objects, and indeed how they are identified. Unfortunately, the instrument that detected it is a missile detection system owned by the US government, and thus very precise data corroborating this fall is classified. But the US government did look at that data and confirmed Siraj and Loeb's findings, and narrowed down a potential search area for the fragments of the meteorite. And that's where the controversy starts. The authors are planning an expedition to try to recover materials from this meteorite fall. This was met with a flurry of skepticism, particularly on Twitter, that such a search can't be done, often citing the disappearance of Malaysia Airlines Flight 370, and just how hard it is to find something missing at sea. This is not a valid comparison, however, and needs to be debunked. Meteorite falls are trackable with enough data, and you can locate meteorite-strewn fields using that data. This can often be narrowed down to a small enough of a search area that fragments can be recovered fairly straightforwardly. In other words, there's a big difference between having data telling you approximately where to look, as opposed to a missing aircraft that could be anywhere in a large swath of the Indian Ocean. Meteorites tend to be magnetic, greatly aiding in their recovery. In fact, at Barringer Crater in Arizona, one of the pioneers of early meteorite research and recovery, H.H. Neininger, used a magnetic rake towed behind a truck in the 1940s to recover not only small fragments of the impactor, the Canyon Diablo meteorite, but also condensed droplets of once molten iron that fell as a kind of rain after the impact event and the formation of the crater. This is of course easier than doing such a thing on the ocean floor, but that's been done too. In 2018, a bolide airburst was detected by the National Oceanic and Atmospheric Administration's NEXRAD weather radar, entering the atmosphere off the coast of Washington state. The bolide was tracked and was observed to have detonated into many fragments, all of them falling into the NOAA's Olympic Coast National Marine Sanctuary, about 16 miles offshore. The detonation, however, was also picked up on seismometers, some as far away as Manitoba. Led by Mark Fries of NASA, the NOAA then mapped the fall area and deployed an ROV and recovered 2 fragments of the meteorite at a depth of 350 feet, lodged in the seafloor. The instrument used to actually recover them was a magnetic rake, and they were very, very small, only a few millimeters. The point here is that you can recover meteorite fragments successfully from the ocean floor, and Mark Fries was instrumental in initially helping to set up the efforts to attempt to recover the CNEOS 2014-01-08 interstellar meteorite fall. But it's also worth noting that the NOAA recovered these materials rapidly after the fall, whereas the fall from 2014 has had significant time to be affected by currents. But this also isn't quite the problem it's been made out to be in popular science articles published recently on this expedition. Here the advantage is depth. This meteorite lies in water about 1.7 kilometers deep, which is a serious advantage. At this depth, the ocean floor is typically unperturbed, meaning that the meteorite debris should still be there after 8 years. Here, the claim in one particular NPR article was that oceanic currents would scatter any materials, as to be hopelessly unrecoverable after just a few years. This is an error on 2 counts. First, drift analysis for the fragments was done by Tim Godier, formerly acting administrator of the NOAA, Marion Alberti of Princeton, and Matthew Harrison of the NOAA, and they were able to calculate for the recovery team the maximum drift rate from the ocean surface to the ocean floor for the meteorite, accounting for the local currents, which was only a few hundred meters. Analyses were also done for the winds at the time, which were weak, and would have had a minimal effect on the fall. Pieces of metal, some very small, have indeed been recovered from the ocean floor many times and in many different places in the world. I generally rarely discuss my pre-YouTube past self. I'm about the subject matter and concepts rather than me per se, but here it fits. Before I did this, for many years I worked in marine archaeology and sea salvage as a historical coin researcher. So let me spin you a tale of what happens to small metallic objects on the seafloor over time. And it involves Spain's once vast colonial empire. During those days, a system was developed for returning revenues to Spain each year from the New World, in the form of vast amounts of gold and silver coins and ingots. Numerous individual ships coming from the colonies would usually congregate at Havana and await Spain sending armed war galleons, usually two, to escort the fleet back to Spain. These two war galleons, one usually positioned at the head of the convoy known as the Capitana, usually commanded by a general overseeing the whole operation, and at the rear an almirante, commanded by an admiral, with most ships in the convoy being heavily armed. In practice, the system varied, but it was the general system. After assembling the fleet, the ships would sail north along the Florida coast until hitting winds that would carry them back to Europe. This scheme usually worked, but there was a wild card that we still deal with today: hurricanes. In 1715, a combination of two treasure fleets set sail from Havana and were caught in a violent hurricane off the Atlantic coast of Florida, indeed generally centered on what is today Cape Canaveral. Most of the ships were lost, 11 of them, with only one French ship that was tagging along that escaped by electing to sail further out to sea, as opposed to the Spanish ships which were hugging the coast. These ships were horribly pummeled and mangled and sank as they were driven into the coastline in shallow water where the currents are constant. This led to centuries of encrusted silver coins, mostly from this fleet, but some from other period wrecks, washing up on the Florida coast to the delight of beachcombers. You would think, after that long, nothing would be left of the ship's cargo in situ after centuries. This was not the case. So even after the Spanish salvage efforts of the period and centuries of active currents, it turns out that the bulk of the coins were still sitting where they sank on the ocean floor, and salvagers were able to secure rights to some of the sites and recover millions of dollars worth of silver and gold coins. In fact, it's one of the few incidences where the original salver, Kip Wagner, uncovered a period map in an archive that literally had an X on it that stated that this is where the Spanish admiral perished in 1715, showing him the general area of the wrecks, which in reality were spread all across the Florida coast, one of which he located floating around on a surfboard that he'd put a window in so he could see the shallow sea floor. Some of these coins are very small, as much as 1.5 grams, and cannot be picked up magnetically. Rather, a system was used to suck up sediment and basically sift out the coins, along with a system of blowing sediment away to uncover objects. This has happened in many places on the ocean floor. Sea salvage of this nature is profitable. The deeper it gets, the lesser the current in general. So you have sites like the Titanic, where pairs of shoes are still positioned together, showing the location of some victims of the sinking. In the Baltic, wooden ships are perfectly preserved with their contents, some dating from the 17th century, such as this one, the warship Vasa, which was raised from Stockholm Harbor and preserved. And there were 3 other Spanish fleets lost around the Gulf of Mexico that were located, including the famous galleon Atocha, which was part of the lost 1622 fleet, which again was lost due to a hurricane. With the Baltic wrecks, it remains one of the hotspots of marine archaeology, and the discoveries so far of perfectly preserved ships haven't even scratched the surface of what's down there. This preservation is because the water is too cold to host ship-boring worms that eat wooden shipwrecks in most parts of the world, and the currents are such that some wrecks get naturally protected. Another area of perfect preservation is the Black Sea, where an anoxic zone perfectly preserves ships that can be 2,000 years old or more with almost no current damage at all. One particularly interesting case is a shipwreck dating from the Mughal period of India's history that was salvaged by none other than Arthur C. Clarke, who was an avid skin diver working off the coast of Sri Lanka when he took off time from writing sci-fi. Here the silver coins had literally been driven into the ocean floor and cemented there by oceanic currents. There's even been suggestions within the salvage community that it may be profitable to recover meteorites from the ocean, using magnets if known fall data is good enough to provide a decent search area, and estimates of the tonnage of meteorite material fallen is high enough. So once again, it's been done. Tiny bits of metal have been recovered from the ocean floor in both deep water and shallow water, and even in areas with active currents. So the debate over whether meteorites can be located on the ocean floor and recovered is moot. And whether you can recover metal from the ocean floor after significant time has elapsed is also moot. They've both been done. The proposition of recovering the interstellar meteorite, while hard, is not anything close to impossible using techniques that have already been employed in other cases. What's actually controversial about this object is that calculations of its density puts it in the upper limits known for an iron meteorite, actually quite high, leading to suggestions that it may be of artificial origin. Well, it's a hypothesis, but only the recovery of material can answer that question. But iron meteorites can be very robust, so we don't want to go overboard. It's also in question as to whether the object was in fact interstellar, but the US government confirmed that it was based on their instrumentation. Unfortunately, they can't release the full dataset without compromising national security by showing off the capabilities of their missile detection system. So the real question is, can the search area be constrained enough to have a decent chance of recovering anything? Maybe, seems so we shall see. But in the relatively distant future, there may be another way to investigate interstellar objects. Overall, Earth is somewhat hostile to meteorites. Weathering, oxidation, the effects of water, and so on degrade meteorite material the longer it sits on the surface. There are some places where meteorite material preserves better than others, but over time the meteorite becomes increasingly weathered and less important scientifically due to contamination. But Earth isn't the only object with a surface in the solar system. Mars, for example, gets hit just as frequently as the Earth. But there, meteorites both have less of an atmosphere to deal with, but also don't suffer the rapid and severe oxidation that occurs to iron on Earth. As a result, several of our rovers have found iron meteorite falls on the surface of Mars. Likewise, there should in principle be interstellar meteorites dotting the Martian landscape that could be recovered and studied should humans found a robust Mars colony at some point. One could also think of other places in the solar system that should be collecting up meteorites, such as any of the moons, or the planet Mercury, or even Pluto. While it may seem a far-off proposition to be recovering meteorites from solar system bodies, the strange thing here is that it's already been done, twice. There's a common theme going on with this video. In the samples of lunar rock and soil brought back by the Apollo missions, a carbonaceous chondrite fragment was found that was mixed in with the lunar soil. While tiny, it was definitely a meteorite that fell on the moon at some point in the past. Had this tiny rock hit Earth, it would have completely burned up high in the atmosphere. But since the moon has no atmosphere, it made it to the surface. But that wasn't the only kind of meteorite found. In lunar rock samples, zircon crystals have been found that aren't consistent with lunar geology, but are consistent with having formed during the late heavy bombardment about 4.1 billion years ago in the Earth's crust. That would make these crystals among the oldest material we have from Earth, and the oldest meteorites, of sorts anyway, ever found on the surface of the moon. This opens up a radical new way to study Earth's early history, which is by studying fragments of Earth deposited on the moon. Zircon crystals particularly can preserve a lot of information about the conditions in which they formed, which means that it's actually more likely to unlock the very earliest history of Earth by doing so on the moon than it is down here where our planet preserves little of its original geology. And there's always the off chance that rocks of even greater importance might be found, such as material ejected from Earth in past impact events, only to be deposited on the moon. It's even possible that materials ejected during the end of the late heavy bombardment might even bear indications of some of the earliest life on Earth, though finding that on the moon would be a stroke of extreme luck. But stranger things have happened. Thanks for listening. I am futurist and science fiction author John Michael Godier, currently concerned for the well-being of the meteorites. They really do have it rough, given that the universe is populated with planets that seem to love eating meteorites. I don't even want to get into what black holes do to incoming material, or how about falling into a star. Very sad for the meteorites. And be sure to check out my books at your favorite online book retailer and subscribe to my channels for regular in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live.